Hello and welcome to this video about projection matrices. These matrices act on a vector so as to lose some of their information. In this example of the simplest projection matrices, they are equal to a diagonal matrix with a mixture of ones and zeros in the diagonal. These are known as standard basis projection matrices. They act on a column vector to make some of their elements zero and the rest kept the same. They can act to make a 3D vector into a 2D vector, becoming a shadow of the 3D vector. So the main property for testing that a matrix is a projection matrix is that its square should be equal to itself. You can see this here because of the nature of squaring a diagonal matrix. Once a projection matrix is applied to a column vector, its elements that weren't zero before are now zero. And if they are multiplied by the same projection matrix a second time, then they're already zero, which doesn't change the column vector. If this matrix is conjugated with a change of basis matrix like this, it will still be a projection matrix, making a shadow of the column vector onto some non-standard basis vectors. We can quickly prove this. We'll start with this expression and square it according to the projection matrix equation. We should get this expression back without being squared. Expanding this expression gives us this. We can gather these terms together into brackets, and they will be equal to the identity matrix because they are a matrix multiplied by its inverse. Then the identity will multiply by one of the projection matrices to the right or left to give us this expression. And these two projection matrices will multiply together to give us this expression. Finally, because E squared is equal to E by the property of projection matrices, then we'll get this expression, thus completing the proof. So any change of basis projection matrix conjugated by a change of basis matrix will be a projection matrix. We can also show that the identity and zero matrices are unchanged by conjugation, so they will always look the same in any basis. So we only need to check that these matrices are not the zero or identity matrices when we check to see if they are projection matrices, if we don't want to include them as being projection matrices. So this is an example of a projection matrix projecting a 3D vector onto a 2D surface so that it loses its y component. So now to create a function to determine whether or not a given matrix is a projection matrix, we'll declare the function with its only internal variable, which is the return variable, and a boolean. And we'll check here to see if it's not the identity or zero matrix, which won't change under conjugation. I decided to define these matrices to not be projection matrices, but you can leave these statements out if you like, if you wish to include them as projection matrices. A projection matrix must be a square matrix in this case where we're defining it, because it must be able to multiply by itself. So then we'll get the square of this matrix, and then we'll test to see whether it is equal to its own square. We'll make the return variable equal to the value of this function, and then we'll return the return boolean variable here. Now to create the square of a matrix function, we'll declare the function with all of its internal variables here. And this matrix must be a square matrix, with the number of rows being equal to the number of columns, so that it can multiply by itself to get the square. We'll put the answer into matrix C. All of its rows and columns will be equal to those of matrix A. And here is the multiplication loop. Matrix A is both the first and second matrix, and different locations will be accessed in A for each element in the product matrix C. Now to create a function to test whether A is equal to C, that is, if A is equal to its own square. Matrices A and C must have the same dimensions to be equal. We'll make up this double loop to look at each element in these matrices. We'll get the positive difference between each corresponding element in these two matrices. And ideally their differences should be zero, but because of numerical errors, they should only be tested to be less than this tiny number. It looks to be quite a large number when we could have taken a much tinier number, but this is the number that works best for this program here. If two numbers are different, we can say that these matrices are unequal and exit the loop. And so we can return this return variable here. Now we have to test this function with examples of projection matrices. This function constructs random projection matrices. We'll firstly construct the zero matrix of size n by n. We'll calculate how many ones to insert into the diagonal here. There must be at least 1 0 and 1 1 in the diagonal. And we'll put some ones and zeros into an array. They are still in order and not mixed up. So now to jumble up all of these ones and zeros, here using the jumble function. And now we'll insert these numbers into the diagonal. Now we have a simple projection matrix in the standard basis. We have to get projection matrices in the non-standard basis. We'll do this by conjugating this matrix with a change of basis matrix. Conjugation is a process of multiplying this newly constructed projection matrix by the change of basis matrix on both sides. We'll calculate a random change of basis matrix here. We'll make up a loop here while the determinant is 0. So we'll get a matrix with a non-zero determinant so that we can find its inverse. So we'll get a random n by n matrix and put it into A. Then we'll copy this matrix to P, being the standard variable to store the change of basis matrix. We'll perform the reducing function on A so as to get it into reduced row echelon form. This will also give us the determinant and its inverse if it has one. We'll check that the determinant isn't too small. If it is, then we'll set it to 0 so as to get another random matrix. And if the determinant isn't 0, then the inverse matrix exists and we'll copy it to Q. We'll repeat this loop if the determinant was 0. And this function will give us a random n by n matrix. We'll make a double loop to go through every location and place a random number in every location of the matrix. Now to create the conjugation function, we have to multiply the given matrix A by a matrix on each side. We'll firstly multiply it by the matrix on the left to give B. We'll set the rows and columns of B. We'll then create the 3 nested loops to carry out this multiplication. Then we'll multiply this product matrix by the inverse of P on the right. Q is equal to the inverse of P. And we'll use the same structured loop to carry out this multiplication, giving us the answer. We can combine all these 4 functions into one function to give us a random projection matrix to put into A. We've calculated it in C, and now we have to copy it to A in the last line of code here. Now we have to calculate an example of a non-projection matrix that's only just a non-projection matrix. We'll write out the code and it will be nearly identical to the code for the random projection matrix up to this part in the code. We'll add a non-zero element to the diagonal in place of a 1. We've stored the number of zeros in R1. We can do this calculation to find the number of ones and find the location to put the non-zero 1 number. We'll reset these 2 counting variables here. We'll make a loop to go through every diagonal element of this matrix. We'll get the location of each element here and increment I for each element in the diagonal. And if the element is 1 at this location, we'll increment the j variable, which counts the number of ones that we've passed. We'll exit the loop when we've passed the rth one. We'll decrement the I variable to land on this location. We'll get a random number to store in it. We'll get it from an array of stored variables rather than as a number from 0 to 9. And here are the sample of numbers we can put into this position. And here is where we actually store the number in the matrix. And if we want to find the value of the change of basis matrix, P, for a particular projection matrix, we'd have to use the normal methods of finding the characteristic polynomial, then the eigenvalues, and then the eigenvectors. But in this case, we already know the eigenvalues, being 1 and 0. So I hope that you have found this video helpful, insightful, and interesting. Please click like and subscribe if you did. Feel free to share this video. Please leave some helpful thoughts in the comments. And thanks a lot for watching.